Did we test them at the end to see if there is a better option from the two of them?
No.
No. So then what type of study is this?
Observational.
It is an observational study since the researcher did not influence anything, did not have a treatment. So this is an observational study since the researcher just observed, just measured different people. This is walking speed, okay? He did not influence anything. Great job. Explain why it is reasonable to use, okay, Welch's t-test is, let me stop sharing. So the t-test is called student's t-test or Welch t-test. Same thing. Okay. So why is it reasonable to use the t-test? So first of all, independent samples and large samples, not 25 or 15.
Can you repeat the question, please? I'm sorry.
Yes, so the question here is explain why it is reasonable to use a student's t-test or Welch's t-test, or the t-test in short. So the samples have to be random, they have to be large, and they have to be independent. Random, large, and independent. Not dependent. We don't care about normally distributed, as long as they are random, large, and independent. Samples are random, small, no, and independent. Do individuals walk at different speeds depending on whether they are departing or arriving? At alpha 0.05, so that's our significance level. Let mu1 represent the mean speed of people departing, and mu2 represent the mean speed of people arriving. State a null and the alternative. Do individuals walk at different speeds depending? It doesn't say faster when they arrive or slower when they depart. It just says different.
So it's going to be A then.
That's it. The key word is here at different. Good. Awesome. Determine the p-value for this test, and also let's determine the t-statistic. Okay, so this time we go to stats, tests, and this is a 2-sample t-test. We have two populations, not proportions, but means. We're testing means, and it's a 2-sample from 2 populations. One population is from people who are departing, and the other one arriving. Definitely independent. Okay, so I will choose 4. And I have the data. I don't have the statistics. I do have the statistics, I'm sorry, not the data. Okay, x1 bar is the departure, 253, and the standard deviation is 49, and sample size 35. So they are both 35. Okay, so now for arrival, 274, and standard deviation 31. And we are choosing differ, not pulled. There is no need for that. And let me see, how do I get to my draw? I want to draw. Is it a 2-tail test? You expect p-value to be in 2 tails, or to be shaded in 2 tails, or 1?
2.
Of course, because of not equal to. Awesome. A tiny p-value. Aha. So the t-statistic, negative 2.1427, and the p-value, 0.0364. Now you know that the p-value is the sum of these two shaded in regions, right? So this piece plus this piece is this. Okay, so where is my problem? Right here. Sorry guys, I have to move you. So round to 3 decimal places, 0.036. Okay, what do we conclude? So let me stop sharing for 1 second. So this is the p-value, and this is alpha. So 0.0364 versus 0.05. Which one is bigger? This is the p-value, and this is alpha.
0.05 is bigger.
Yes. So the p-value is smaller than alpha. What do we do in this case?
Fail to reject.
Careful, careful. Remember always, right? If this is alpha, and this is the p-value.
Oh, sorry. Yeah, you're right. Reject.
Yes, but it's fine. That's why graphing it is always, that's why I always go for the graph, right? But what the calculator, thank you so much. What the calculator cannot do, because it doesn't know, it cannot perform the comparison for us. We don't have a way of entering alpha, right? So that's why we have to be careful when alpha is greater than this number. Then the z statistic in this case, sorry, the t statistic in this case is in the rejection area. So this will be alpha. Half of alpha will be this area, and the other half of alpha will be this area. So this piece is smaller than half alpha, or the entire p-value is smaller than alpha. So we reject the null hypothesis. Where's my problem? Right here. So let's read carefully. Obviously, we cannot read. There is no need to read C and D because we have to reject the null hypothesis. There is sufficient evidence to say that travelers walk at different speeds, depending on whether they are arriving or departing. We don't know which one is higher because that's not the purpose of the test. The test is just saying, are they the same speeds? And it appears that they're not. And the sample says, if I select a different sample later on, I may find different things. But from this particular sample, there is sufficient evidence. I reject the null hypothesis. There is sufficient evidence at this level of significance to say that the travelers walk at different speeds depending on blah, blah, blah. Okay. So a researcher wanted to determine if carpeted rooms contain more bacteria than uncarpeted rooms. The table shows the results. Okay, so this time, let's select what we want to choose because I like to work on StatCrunch with this problem. Determine whether carpeted rooms have more bacteria than the uncarpeted ones at alpha 0.05. The reason why they're saying that the normally probability plots indicate that the data are approximately normal is because look at the sample size. 3 plus 3, 6, 8. For such a small sample size, we need normality. For larger sample size, we're fine. So there are no outliers, they say, and data is approximately normal. So we can use the t-test. But which one? Can anyone identify which one? So mu1 greater than mu2. Awesome. Excellent. Thank you. Good. Determine the p-value. So with StatCrunch, we have to go to the t with 2 samples and data. Stats, t statistics, t stats with 2 sample and with data. And sample 1, carpeted. Sample 2, uncarpeted. We want greater than. See, StatCrunch does not use mu1 equal mu2 and mu1 greater than mu2. It moves mu2 to the other side. Okay, so let me stop sharing for a second. So the null hypothesis is mu1 equals mu2, but StatCrunch, as I mentioned with proportions, writes this, which is they are identical. And the alternative in our case is mu1 greater than mu2, but the StatCrunch moves mu2 to the other side and uses this. They are identical. Okay, back to sharing. And we want hypothesis testing. And yes, that's correct. Output show critical value. I want to see the critical value. I want the significance value to be at this and store in a data table. I don't need that. Okay. So the t statistic is 0.377348. We don't need that many. The p-value, the critical value is if we calculate by hand. I just wanted to see it. That's the t critical value, and not the t statistic coming from the sample, but the t critical value for the number of degrees of freedom. Okay, so we only need the p-value, which is 0.3559. Back to the problem. Where is my problem? What is this? Oh yeah, okay. So the p-value, round to 3 decimal places, 0.356. And then it's going to ask us, I'm sure, to draw a conclusion. So let's draw a conclusion. Let me stop sharing for a second. So the p-value is, oh, I don't have to write it again, it's right here. So an alpha is 0.05. What do we conclude? Alex, what do you think we conclude on this?
You would fail to reject.
Absolutely, because the p-value is greater than alpha. Brilliant, thank you. So we fail, we do not reject. So if we do not reject, there is not significant evidence at alpha 0.05 to conclude that the carpeted rooms have more bacteria than uncarpeted rooms. Okay? We don't have significant evidence to reject because the p-value is greater than alpha. We fail to reject. We do not reject the null hypothesis. There is not significant evidence from this sample of carpet or non-carpet, right? Maybe with a different carpet, it's a different story. I don't know. But we fail to reject the null hypothesis, or we do not reject the same thing. We do not reject or fail to reject same thing. We do not have sufficient evidence to conclude that carpeted rooms have more bacteria. Great job. Okay. The following relationship holds between hypothesis tests and confidence intervals. So we talked about this last time, but let's talk about it again. So for a two-tailed hypothesis test at the significance level alpha, the null hypothesis will be rejected in favor of the alternative, not equal to, if and only if the level of confidence does not contain 0. Okay, so let me explain this again. If the null hypothesis, that's my page 4. If the null hypothesis is mu1 equals mu2, and the confidence interval, whatever, let's say 95, doesn't matter. Confidence interval has, let's say, 31.2, comma, 40.2. It means that mu1 minus mu2 is consistently positive, which means mu1 is greater than mu2. In other words, mu1 greater than mu2, because the answer is always positive. If I have, let's say, another 95 confidence interval and I have negative 40.5, comma, negative 2.3, what is the situation with mu1 minus mu2? Well, mu2 is bigger. So this is less than 0, right? Because mu2 is bigger. So when I subtract these two, I always get a consistent negative number. Well, this has a positive in front. If this were bigger, I would have gotten a consistently positive interval. When this is bigger, I get a consistently negative interval. So this is bigger than this. What happens in another last option? Let's say a 95 confidence interval is between negative 20 and positive 10. Then mu1 equals mu2 cannot be rejected. Here, the null hypothesis is rejected. Okay? Because the difference of these two is always positive, or appears to be 95% confident that it's positive. So I'm really telling you that this is bigger than this, not equal to. So reject. Here I'm really telling you that this is bigger than this, not equal to, so reject. But here I cannot tell you to reject that mu1 equals mu2. Why? Because there is 0 in the middle, somewhere. Not the middle, not necessarily. 0 is in the interval. 0 is in this interval. So I don't know which one is bigger, or maybe not. But conclusion is that I cannot reject, cannot be rejected. H naught, of course, cannot be rejected. So back to the problem. So for a two-tailed hypothesis, okay, will be rejected in favor of the alternative, will be rejected, as I mentioned, in favor of the alternative if mu1 minus mu2 does not contain 0. So in the top two examples, plus and minus, 0 is not there. So I have to reject the null hypothesis because it appears that consistently one or the other is bigger. But if the interval contains 0, then I'm stuck. I'm stuck with the null hypothesis. I cannot tell you which one is bigger. Okay? It appears that they are the same. In each of the following cases, illustrate the preceding relationship by comparing the results of the hypothesis test and confidence interval. Okay. So they are giving us, I'm going to copy them. I'm just going to copy A and then stop sharing and so on and so forth. So I have mu1 equals mu2. They're giving us alpha 0.05. What is that p? I'm assuming is the p-value, 0.362. And the confidence interval is negative 4.92, 1.77. Okay, so and then for this two-tailed test hypothesis test based upon the given p-value. Okay. Oh, okay. So let's talk about it first. So this is alpha, and this is the p-value. Forget about the interval for a moment. Don't look at the interval. So alpha and p-value. What do we conclude? do we reject or fail to reject the null hypothesis?
Fail to reject.
Yes, fail to reject. When we fail to reject, should 0 be in the interval? Yes? And so is here. So these two are support each other. So the p-value is bigger than alpha. So we fail to reject. And we fail to reject if 0 is, we fail to reject this if 0 is in the interval, and it is. So then, for this two-tailed hypothesis test based upon the p-value, okay, you already told me do not reject, fail to reject or do not reject is the same thing, the null hypothesis, since the confidence interval contains, does contain, since the confidence interval does contain 0, it supports the conclusion that the population means may be the same. Now here, the confidence interval is consistently negative. Which of these two will be bigger if it's consistently negative? For this two-tailed hypothesis test based upon the p-value, see the p-value is smaller than alpha. We have to reject the null hypothesis since the confidence interval does not contain 0. It supports the conclusion that population means may be different. Yes. And because it's consistently negative, the second one is bigger. Any questions? Any questions?